So today we are covering the nilpotent radical of a Lie algebra. So we're going to have our Lie algebra BG as always. The nilpotent radical as opposed to the regular radical, which is solvable. So this is kind of a thing of G is the intersection of the kernels of the finite dimensional representations of G. I have some remarks to go along with that. First off, we're going to have S be the nilpotent radical of G. As every decreasing sequence of vector subspaces of G is stationary, there exists a finite number finitely many finite dimensional simple representations of G whose kernels have intersection S. The direct sum of these representations is semi-simple as the sum of simple representations and has kernel S. Thus, the set of kernels of finite dimensional semi-simple representations of G has the least element which is of course going to be S. Okay, now secondly, by our previous proposition, S is the intersection of the largest nilpotency ideals of the finite dimensional representations of G. S is contained in the largest nilpotent ideal, which is not the radical, as I thought it was, of G, and is therefore, and is so, a nilpotent ideal of G. Condition number 3. Every linear form lambda on G with it being on the derived algebra of G, which is G bracket G is just 0, is a simple representation of G. So lambda of S must be 0. Thus, S is in the derived algebra of G. We saw in our previous remark that S is in R, which is the radical of G. We will see that the nilpotent radical is the intersection of the regular radical with the derived algebra. Let V be a finite dimensional vector space on K. G in GLV a subalgebra, so this is a linear algebra, such that V is a simple G module. But let me try that G again here. And finally, we're going to have A be a commutative ideal of G. Then, the intersection of A and D of G is 0. We're going to, as always, let S be the subalgebra of the linear maps in V, generated by 1, and in this case, our commutative ideal of G, A. If B and G is an ideal of G, contained in A, such that the trace of BS, we'll call it B prime S prime, just because the notation is ugly there, equals 0 for, of course, all B prime in B, S prime in S. Then, by the definition of S, we see that the trace of B to the N is 0 for all integer n greater than 0. Hence, B is nilpotent. I mean, we can see that our S prime in this first equation can just be like 1, for example. It's really reflecting on the conditions of B. So, by our previous corollary, B is just 0. Oh. We first apply this to the bracket of G and A and G, which is an ideal. For X in G, A hat in A, S hat in S, the trace of X in A hat, this element X in A hat times S is equal, S hat is equal to the trace X A hat S hat minus A hat X S hat, which is equal to the trace of, since X is gonna just split out here, we get X and AS. can rewrite this as minus SA, which of course is going to be equal to 0 since AS is SA. Hence, by our previous result, the bracket of G and A is just 0. Hence, G commutes with A, and thus with S. For X and Y and G, and S hat and S, similarly we have that the trace of the bracket of X and Y times S hat is equal to the trace of X, Y, S hat minus Y, X, S hat is carrying on the trace of X times Y, S hat minus S hat Y. I think what's happening here is we're just rotating the second term and then factoring everything out. And this is of course just 0. Then taking B to be the ideal of the derived algebra of G intersection with A, we are done. That was our lemma. And now we said in the remarks that we were going to show that for a Lie algebra G with radical R and nilpotent radical S, that S is equal to the intersection of the derived algebra of G and R. And we have from our remarks that S is inside of the intersection of the derived algebra of G and R. So we just need to show proof. We only need that if rho is a finite dimensional simple representation of G, then rho of dg intersection R is 0, which will put dg intersection of R in the kernel of a representation, and therefore of an arbitrary representation, and therefore inside of S. So let K be the least non-negative integer such that rho of the K k plus 1th derived series element of R is 0. Writing G prime as row of G, A prime as row of dk of R, now as dkr is an ideal of G, A prime is an ideal of G prime, and this is A prime is actually commutative, as we have that row of dk plus 1 of R is equal to 0. If V is the space of row, G prime is contained within the general linear Lie algebra of V, and V is a simple, because row is simple, G prime module. Then row of the intersection of the derived series of G, derived algebra of G, and the kth derived algebra of R is inside of the derived series of derived algebra of G prime, intersecting with the A prime, which is 0 by our previous results. If k is greater than 0, then the kth derived series of R is inside the derived series of G, and row of the kth derived series of R equals 0, but we said that k is the last one that will be not 0. So this is a contradiction. This k is 0, and row of dg intersection of R is equal to 0. And we're done. Now we only have 7 corollaries left, so let's go through all those. Sure, that won't take too long, right? Corollary number 1. Let G be a solvable Lie algebra. Then the nilpotent radical of G is the derived series, derived algebra. If rho is a finite dimensional simple representation of G, rho G is commutative, and the associative algebra generated, I guess we're going to call it L, generated by 1 and rho of G is a field of finite degree over K. Let me switch over here. And our proof. Here, R is just all of G. So S is obviously just equal to the derived algebra of G. So rho of the derived algebra of G has to be 0. So G prime being rho of all of G is commutative. Don't know why we bothered naming rho of G in this context. And so every non-zero element of L is invertible by Schur's lemma. So L is a field. Now I actually do want to go back and just check something real quick. So the radical, if you recall, is the largest solvable ideal. Since G is solvable, then that's just all of G. Yeah, okay. I just need to verify that, but yeah, that's pretty easy. Corollary number 2. This is also known as Lee's theorem, named after my man Sophus, I'm presuming. So we're going to let G be a solvable Lie algebra. Over an algebraically closed K. Let M be a G module of finite dimension over K Didn't need that hyphen, but whatever. With a Jordan Holder series of mi from 0 to r. Then mi minus 1 over mi is dimension 1 over k. And for all x and g, x on mi minus 1 over mi is equal to lambda I x of x acting on 1, where this lambda I is a linear form on G, which is 0, on its derived algebra. And so we get that every simple G module of finite dimension over K is dimension 1. So we're going to let rho I be the representation of G on mi minus 1 over mi. The associative algebra Li generated by 1 and the image of G under rho I is a field. Finitely extending K and so is K. Mi minus 1 over mi is a simple Li module so dimension of mi minus 1 over mi is 1. And that's all they bother proving here, so that's all we'll bother proving here. Okay, and quick remark. If the sequence mi is replaced with another Jordan holder. Then the sequence of linear forms on GLI is permuted by the Jordan holder theorem, because essentially we're just like rearranging how we're decomposing our space M. And oops, another remark. Let EI from 1R be a basis of M such that EI belongs to MI minus 1 but not MI. If X is in G, the endomorphism of M corresponding to X is represented with respect to this basis by a triangular matrix with diagonal coefficients of lambda I of X from I equals 1 to R. Corollary. Sorry, I spaced out there for a minute. Suppose K is algebraically closed. If G is an R-dimensional solvable Lie algebra, every ideal of G is a term of a decreasing sequence of ideals of dimension R minus 1 all the way down to 0. And this is our third corollary and the proof. Every ideal is part of a Jordan holder series of G as the space of the adjoint representation. From which we get the Lie's theorem applies, and we are done. Okay. 4 more corollaries to go. Corollary 4 here states suppose our field is just the reals. let G be a solvable Lie algebra every simple representation of G is dimension of at most 2. Every ideal of G is a term of a decreasing sequence with a gi from 0 to m of ideals such that GO is G, changing the way I'm holding my pencil again, GO is G, GM is nothing, and the dimension of GI minus 1 over GI is at most 2. And they don't really bother proving this one from corollaries 2 and 3, with the fact that every algebraic extension of R is of degree of at most 2. So I'll just write it down. Every algebraic extension of our double line R is degree of at most 2. Corollary. A Lie algebra G is solvable if and only if its derived series, if its derived algebra is nilpotent. This is necessary. We've already done the necessary part, which is our first corollary, which said that the nilpotent radical of G is the derived algebra. The nilpotent radical of a solvable Lie algebra is its derived algebra. And our proof essentially then is sufficient because G over its derived series is commutative. Corollary. Number 6. Let rho be a finite dimensional representation of a Lie algebra G. I'm gonna let something happen, I'm sure. Let R be the radical of G. then every x in R such that row of x is nilpotent belongs to the largest nilpotency ideal n of G. Proof. Let V is going to be the same kind of setup we've seen before. V is the space of row with Jordan-Holder series Vi from 1 to R for the R module structure. This is the Jordan-Holder series for the R module structure on V. And let row I be the representation of R with space Vi over Vi minus 1. If row x is nilpotent, then we need to show that it's in the largest nilpotency ideal. So is row I of x as for all I, the algebra generated by row I of x is a field. This is a different thing. So if row of x is nilpotent, so is Pi of x. And since the algebra generated by row I is a field, it must be 0. Row I of x, that is. Conversely, if row I of x is 0 for all I, annotation. My writing I'm still not used to is for all I, then obviously row x equals 0. Thus, the set A of x in R such that row of x is nilpotent. I'm out of space. This set A of x in R such that the row of x is nilpotent is an ideal of R. Also, the bracket of G and A must be within the derived series of G, intersecting the radical inside of the largest nilpotency ideal intersecting the radical inside of A. So A is an ideal of G. Thus A is N, belongs to N. There we go, and that's our 6th corollary. One more, it looks like it's going to be pretty short, and then we are free. Let G be a Lie algebra with a radical R. The following are identical as sets. The largest nilpotent ideal of G, the largest nilpotent ideal of R, the set of X in R such that the adjoint in G of X is nilpotent. D, the set of X in R such that the adjoint of X on R is nilpotent. And these are our 4 equivalence sets. Oh, wrong button. Proof. We have A is inside of B, has to be inside of D, has to be inside of C by definition. And then we have C is inside of A by our previous corollary. On the adjoint of G. And we will call it there. Lots of little things we've done. I think we did about that long, so maybe one more video on solvable algebras, and then we'll be getting into semi-simple algebras. And after that, I think everything's gonna get crazy, so look forward for that.